Capacity Requirements Planning (CRP) is a detailed capacity planning process that validates whether sufficient production resources are available to support material plans generated by Material Requirements Planning (MRP). Within the Manufacturing Planning and Control (MPC) hierarchy, CRP operates below Rough Cut Capacity Planning (RCCP) and works directly with planned and released orders generated through MRP. While RCCP focuses on validating the master production schedule at a high level, CRP performs detailed analysis at individual work centers and resource locations. Its primary purpose is to ensure that labor, equipment, facilities, and critical resources can support planned workloads. Effective CRP improves schedule feasibility, enhances resource utilization, and strengthens operational execution throughout manufacturing operations. The CRP process follows a structured sequence of activities that begins with inputs from MRP, routing information, work center data, and production standards. Planned and released orders are translated into capacity requirements using routing data that specifies the resources and processing times required for each operation. The system then calculates workloads for individual work centers and compares these requirements against available capacity. Capacity reports highlight overloads, underloads, and potential bottlenecks requiring management attention. Planners analyze the results, evaluate alternatives, and implement corrective actions when necessary. Through this process, CRP provides visibility into future resource requirements and supports informed decisions regarding production scheduling, workforce planning, and capacity management. CRP offers several advantages while also presenting certain limitations. Major benefits include improved visibility into resource utilization, better identification of bottlenecks, enhanced schedule feasibility, and stronger coordination between material and capacity planning. CRP enables organizations to identify problems before production begins, reducing disruptions and improving customer service performance. However, CRP depends heavily on accurate routing data, production standards, inventory records, and schedule information. Inaccurate data can lead to misleading capacity projections and poor decisions. Additionally, CRP assumes that planned processing times and resource availability remain relatively stable. Despite these limitations, CRP remains an essential tool for managing detailed production capacity and supporting effective manufacturing execution. Production authorization decisions represent critical control points within the planning process. Before releasing orders to production, organizations must verify material availability, capacity sufficiency, engineering readiness, quality requirements, and customer priorities. Various situations may require adjustments to committed resources, including equipment failures, labor shortages, supplier disruptions, engineering changes, demand fluctuations, or unexpected customer requirements. Preventing such situations requires proactive maintenance programs, workforce development, supplier management, contingency planning, and effective communication across functions. When disruptions occur, planners may need to adjust schedules, reallocate resources, authorize overtime, subcontract work, or revise production priorities. Effective management of these decision points helps maintain schedule integrity and operational performance. Customer order promising is closely linked to capacity planning because organizations must evaluate available resources before committing to delivery dates. Order promising decisions require visibility into inventory levels, production schedules, capacity availability, supplier commitments, and transportation capabilities. Available to promise ADP and capable to promise CTP methodologies help organizations determine whether customer orders can be fulfilled within requested timeframes. Resource allocation decisions become particularly important when demand exceeds available capacity or supply. In these situations, organizations may prioritize orders based on profitability, strategic importance, customer relationships, contractual obligations, or service commitments. Effective order promising improves customer satisfaction while ensuring that operational commitments remain realistic and achievable. Final Assembly Scheduling (FAS) translates customer demand into detailed assembly schedules, particularly within assemble-to-order environments. Sources of demand considered in FAS include customer orders, forecasts, replenishment requirements, backlog, promotions, and distribution needs. Product flow analysis, commonly referred to as VATI analysis, helps organizations understand product structure and process flow characteristics. V-shaped structures involve multiple components converging into fewer finished products, while A-shaped structures involve a limited number of inputs diverging into numerous finished products. T-shaped and I-shaped structures represent other manufacturing flow patterns. Understanding these product structures supports effective scheduling decisions and resource allocation throughout the final assembly process. Developing and maintaining the final assembly schedule requires continuous evaluation of inventory levels, backlog, capacity availability, major customer orders, engineering changes, time fences, product designs, and incoming supplies. The FAS process involves reviewing demand, verifying resource availability, allocating capacity, scheduling assembly activities, and communicating commitments across the organization. Actual performance must be monitored regularly to ensure alignment with planned schedules. When significant deviations occur, planners may need to revise schedules, adjust priorities, or reallocate resources. An unrealistic FAS can lead to missed deliveries, excess inventory, production disruptions, increased costs, and customer dissatisfaction. Effective management of the FAS ensures that final assembly activities remain synchronized with customer demand, material availability, and organizational objectives while supporting reliable operational execution.